Hi, in this video, what I would like to show you is what the data path does and how your data path is supposed to work for your 4-bit CPU. So again, this is your figure of reference. You always want to start off at this location. And let's take a very simple example. Let's say that whatever value that you have on your switches, um, let the value be 1010, right? 1010. And let's say that we want this value to get stored into my R2, right? So then the series of steps that I will need to follow is first, I will need to input 1010 on my slide switch, after which I first need to enable this tri-state buffer. So if I enable this tri-state buffer, my value 1010 is now present on my bus, my 4-bit bus. Okay, so actually before I do this, right, I want to make sure that all of my tri-state buffers, all of initially, so we'll call my initial state, all of my tri-state buffers have to be reset. So if let's say that this all the tri-state buffers are enabled when there's a 1 on the control line. So initially what I want is I want all of the control lines to be 0, which means that all my tri-state buffers need to be disabled. That's the initial state. Next, what I want to do, I want to load the value 1010 on my switches, and then I want to enable this control line so that that value goes through my tri-state buffer and is on my 4-bit bus. Good. So once I know that my value is on my 4-bit bus, so let's say that is one clock cycle. The next clock cycle, what I would want to do is I want to enable this tri-state buffer, right? So then what will happen, my data which was available on the switches is now on the bus, and for my bus, it is available at the D input or the data input of my register R2, right? After which I will have to enable the R2 enable, right? Just like R1 enable, this is my R2 enable. So if I now enable my R2, that value, which is 1010, will be stored on my register R2, right? So there are two ways of thinking about this. One is you enable this control signal. You first set your value, and then on the first clock cycle, turn on this control enable signal, so it's on the bus. On the second clock cycle, you turn on this control signal, so the value which is on the bus is available at the data input, and on the third clock cycle you turn on the R2 enable, and so on the fourth clock cycle, which is the next clock cycle of R2, your data is going to be stored in your register. So that is one way of doing it. The other way of doing it is, since you see these are just tri-state enables, tri-state buffers, right? Uh, a way of optimizing this would be to turn on both of these tri-state buffers on the same clock cycle. So you set the value of your switches, and immediately this tri-state buffer is turned on and this tri-state buffer is turned on. So what will happen is your value will immediately go onto my bus, and from there will be available at the data input of my R2, and then when you turn on R1, R2 enable on the next clock cycle, that value is going to be stored in your register R2. Okay, so these are all optimization tricks. In your case, you don't have to worry about how many clock cycles you use to load your R2 in. If you take 3710, that will become important. For now, your only concern is to make sure that whatever instruction. So in this, for example, this instruction that we have executed is nothing but load R2 with whatever is your input. So load R2 with whatever value you have over here. Okay, and so now let's say that you want to load something into R1. It's basically the same stuff, right? You load the new value into your S3, S2, S1, S0, turn on your so let's say after loading R2 you want to load into R1. The first step you need to do is disable all the tri-state buffers, right? After which you load the new value onto your switch, you turn on this tri-state buffer, so the values are available on the bus. You turn on this tri-state buffer, so now that value is available at the D input of R1. Turn on R1 enable so that the value is stored in your register R1. Again, doesn't matter how many clock cycles you take, as long as you're able to get the value into your R1 and R2. Good. Now, once you have the value in your R1 and R2, let's say you want to perform an add operation, right? So again, you know that your ALU has 4 operations: add, OR, XOR, and NOT, right? So you need to provide the appropriate control signal. So let's say a 00 stands for add operation. I'm just, assigning one sequence. So then if you provide 0, 0 at this point, the 4-bit value in R1 and the 4-bit value of R2 will be taken, and you will perform the add operation on it. And that value is going to be available at the data input of my R out, right? It's available at the data input of R out. It's still not read in. The reason being my R out enable is not turned on yet. So if I want to read that value, which is the output from my 4-bit ALU into R out, I need to make sure my R out enable is turned on, and so that on the next clock cycle, the value of whatever ALU outputs will be stored in my R out. Again, because this tri-state buffer enable is disabled, it's only stored in my R out. It is not going to my bus, right? So the only important design principle that you need to keep in mind is that everything should make sense. There should be like a clear flow. Think of it like water flowing, right? There should be very clear paths and very simple flow. If it makes sense to you, and if it's very clear to you, then it probably works. You shouldn't really make any random guesses and just hope designs work. Doesn't happen that way. Okay, so now let's say that you have this R out, and this might be a little tricky, but let's say you want to write this. This is called a write back operation. What this does is you want your R out value to go back into R2. Okay, this is just a write back. Also, this is also called as a save operation. Some people call it a move or a load operation. There are many complicated ways, but it's just a write back, right? So what you do again, all your buffers should be disabled. Then you first enable this tri-state. So whatever the value of your R out was is now on the bus, right? And then what you do on the next clock cycle, enable this tri-state buffer. So that value which is on the bus comes to the data input of R2, turn on R2 enable, so that on the next clock cycle, whatever the value of an R out which was on the bus is now stored into my R2. So my write back is now complete, right? So on in paper, this is again a 3-cycle process, right? First cycle you turn this guy on, second cycle you turn this guy on, and third cycle you can read it into your R2. If you want to optimize it, you basically turn on both the tri-state buffers in one clock cycle, so that on the next clock cycle you will read that value into R2. So these are all, once you have an initial working design, you can do mix and match. So this is basically a data path. This very simple data path. Okay. What else do we have? So let's take, for example, this one, the approach, right? In the first week, your objective would be the design of your ALU data path unit, that is in figure 1, and to hook it up together. That is, you have your ALU and your bus and your registers and your tri-states. So basically just connect it in this particular configuration. Okay, again, keep in mind this has to be hierarchical design, guys. You build your ALU as a separate module, your registers as a separate module, your tri-state buffer as a separate module, and then tie all of them together in hierarchy, just like you did for lab 4 and lab 3. One way to test your data path is to do the following, right? So again, this is one way. This is not the only way. You can also come up with a test sequence of your choice. So for example, what I explained right now, right? Loading a value into R1 and R2 and then adding those together. That's a particular test sequence. And then you want to write back R out into R2. That's a different test sequence. You can also do a write back of R out into R1. That's a third test sequence, right? So you want to, you can come up with such simple test sequences yourself and make sure that you're able to, the data path flows correctly, right? You always want to start simple. The simplest the case that we started was we just wrote a value into R2, right? It's a very simple 3-cycle process. Next, what you do the same with R1. So if R1 and R2 now hold the value whichever you're writing from your switches, then you know that this cycle, this path works. Then what you do, you set your ALU control, and if ALU control performs the correct operation, right, then your ALU works. How do you know that your ALU works? Because you will have to check, you'll have to monitor the values of R1 and R2 and R out, right? There is no doubt about it. You'll have to monitor all the designs, but you can, sequentially, step by step, see if all of your design works. That's the benefit of writing test benches. So initially what he says, you want to reset your R1 and R out, which is go to 0. So actually this is not just R1 and R out, you want to reset all the 3 registers. So R1 and R2 and R out are initially supposed to be reset. So that means they're all going to 0. Next, what you do, you want to load the value of R2 with 0, 0, 1, 0. You want to load R2 with the value 0, 0, 1, 0. So what do you do? you first set your switches to 0010, and you enable these two tri-state buffers, and then you enable your R2 enable, and you should see that R2 will end up getting the value of 0010. Again, this is in your model sim, guys. This is you for week one. I don't want you to put anything on your board and test. Okay, I know that it's a simple design, but if you put this on your board and test, you will have to then wire a lot of your enable signals and tri-state buffer signals onto your board. It will become very messy. So just do this in models. You also need to get good practice on testing it. Next, clock cycle one. So clock cycle one basically means in your first clock cycle, because this is reset, right? In your first clock cycle, you want to load external data, which is 100 into R1, and other registers get disabled. Good. So that is your first clock cycle. Or rather, first you reset, and then you load the value of R2 with 0010, and then it's the same thing. 100, enable this tri-state, enable this tri-state, enable R1. So then the value of 100 gets loaded into R1. Simple. Then the next clock cycle, you set your ALU control to the perform add sequence. You perform your add operation. In our case, it was 00, right? You can again encode it any way you want, and then you want to enable your R out. So if you perform your add control sequence, you basically end up adding the decimal value 8 plus 2, which gives you your result as 10. So your R out should hold the value of 1010. Then you can stop your simulation and watch the data stored at R out. So again, in this case, because 8 and 2, you will end up getting R out as 10. You can, do bigger numbers, of course, nobody's stopping you. And you can also do different operations. You must do different operations, right? You just testing add is not enough. You want to test all your ALU operations. So that is it for your data path and understanding how your data path should work. Good luck.